Welcome everybody. We're going to be doing section 1.2, Basic Ideas and Terminology. This is a more formal introduction to some of the equation types that we're going to be seeing. So let's start with a definition. A linear differential equation of order n, sometimes we would call this an nth order linear differential equation. This is a differential equation that can be written in the following form. So we can write it this way. A naught of x times y, nth derivative of y, plus a1 of x times the n minus first derivative of y, and we just keep going down. A n minus 1, this is the n minus first function of x, times y prime, plus a n of x times y is equal to capital F of x. Okay, I will call this star. It's important to pay attention to what we're saying here. We're saying that a linear differential equation of order n can always be written in this form. You've got an nth derivative plus an n minus first, and they go all the way down. And you've got functions of x being multiplied by every y. Okay? Now, it is possible that some of those functions will be 0, so not every term has to appear. Okay? And it's also possible for any of those AIs, those functions, to be constant, non-constant. They might be linear, but they might not be, and that's okay. The only thing we require is for the y's to look like this. Okay? A differential equation that can be written. Oh, there is one thing I need to say about the above, is that, of course, we are assuming that a naught of x is not 0. Because if it were 0, this wouldn't be nth order, okay? So we do need to have a non-zero first term there. A differential equation that cannot be written in this form for any n is called a nonlinear differential equation. Okay, so nonlinear stuff is pretty complicated. We're only going to be dealing with a few types of nonlinear differential equations, very special cases. Most of the time, we're going to be dealing with linear. So let's do an example. We'll do this on the next page. Let's do some classifying. Classify each differential equation by its order and whether it's linear or not. So first, y triple prime plus 3e to the x y double prime plus x cubed y prime plus cosine of x times y is equal to ln of x. Okay, so looking at this, we notice that every y is to the first power. right? And we do have some nonlinear stuff going on, but it's all in the x's. In other words, it is linear, and this is third order. So let me write this down. This is third order linear differential equation. Third order linear. Okay. Let's do another one. How about xy prime minus 2 over 1 plus x squared y is equal to 0? Again, even though we have nonlinear functions, they're all in the x's, and so the y's are written in a linear way. So this is a first order linear, right? We only have one derivative there. Okay, how about this one? Y double prime plus x to the fourth cosine of y prime minus xy is equal to e to the x squared. This guy is trying to deceive you, right? It almost looks like it follows that form, but the problem is this right here. We're taking a cosine of y prime. This is nonlinear because of that. Okay, everything else is fine, but that makes it nonlinear. So this is also second order because we have the second derivative. So it would be second order nonlinear differential equation. Let's do another one. How about this? Y double prime plus y squared is equal to 0. It's definitely second order, right? Is it linear? No. We have a y squared. So it is nonlinear, right? Nonlinear differential equation. Okay, one more. How about this one? Second derivative of y with respect to t plus omega squared times y equals 0. Second order because we do see a second derivative. And this is linear, right? Because the y's or the derivatives of y are not being squared. So this is a second order linear differential equation. Okay, let's go to the next part here. So we have a definition. A function y equals f of x, or we're also going to call it y of x. This is a lot nicer to write down. That is at least n times differentiable on an interval I is called a solution to star if the substitution y equals f of x y prime equals f prime of x, and nth derivative is equal to the nth derivative of x in star reduces it to an identity valid for all x in I. Okay, so a function that when you substitute all of these pieces in other words, you take a function and you calculate all of its derivatives and you plug it in for the y in the differential equation. And if you plug it in and it reduces to an identity, remember an identity means it's always true for every x, then we say y is equal to f of x satisfies the differential equation. Or we say f of x is a solution to the differential equation. These are just different ways of writing it, okay? Is a solution or satisfies. Okay, so let's do a quick example here where we verify that something is a solution, okay? So, verify that for all C1, C2 that are real numbers, y of x equals C1 e to the 2x plus C2 e to the negative 2x is a solution to the differential equation y double prime minus 4y is equal to 0. So we are trying to check that this function right here is a solution to this differential equation. So the way you do that is by taking as many derivatives as you need in order to plug it into the differential equation. So let's go ahead and take a couple of derivatives, okay? So what is y prime equal to? Now notice y prime doesn't appear in the differential equation, but y double prime does, so we do need to find the first and the second derivative. So the derivative, using the chain rule, is 2c1 e to the 2x minus 2c2 e to the negative 2x. And now let's take a second derivative. This becomes 4c1 e to the 2x, and then this becomes plus 4c2 e to the negative 2x. Okay. Now what? Well, let's go ahead and do our substitutions, okay? So what we're going to do is we're going to take y double prime, substitute it in for y double prime in here, and then we're going to take y, let me go ahead and make that a different color. We're going to take this y right here, and we're going to put that in here, and then we're going to see if that differential equation becomes an identity, okay? So plugging in, we get 4c1 e to the 2x plus 4c2 e to the negative 2x minus 4 times y So the question is, does that equal 0? I put a question mark there because until we're sure they're equal, we're not going to write the statement down. But let's see what we get here. This is 4c1 e to the 2x plus 4c2 e to the negative 2x. On the left, we get negative 4c1 e to the 2x. We're distributing here, this and this. and then minus 4c2 e to the negative 2x. And this guy cancels with this guy, and this guy cancels with this guy, and so we get 0 equals 0, so it works. So let me just say the stated y of x is a solution. To the differential equation. Okay. So it shouldn't be too difficult to check whether something is a solution or not. Now the same thing works implicitly, so let me do another example. Verify that the relation x squared plus y squared minus 4 equals 0 defines an implicit solution to the nonlinear differential equation dy dx is equal to negative x over y. Now this is nonlinear because there is no way of writing this in the other form because of the y being on the bottom like this, okay? Y being on the bottom makes this thing nonlinear. We're dividing by y, so that's like y to the negative 1, right? Okay, so how would we solve this? Or not solve rather, but how would we check? Well, we need to find dy dx. So for finding dy dx to plug in, use implicit differentiation of the curve. Okay, so the curve is over here. We want to do d dx of this guy. Okay, so if I do d dx of that, I end up with the following thing. I have 2x plus 2y times dy dx is equal to 0. Or this is the same as dy dx is equal to negative 2x divided by 2y, which is the same as negative x over y. Now, we just divided by y, so we need to be careful to note that we just threw away a potential solution of y being 0. However, if you look at the original equation, the way it was written, y is not 0. So let's not worry about it, right? Because if y were 0, we wouldn't even have a differential equation to begin with. So we get dy dx is equal to negative x over y. And this is what we're going to plug in for this guy, right? We're going to take this guy and put it in there. And we notice that it works, right? Because when we take that guy and put it in, we actually have the exact same thing on both sides. So it works. So therefore, it is a solution. Okay. So what does it mean to have a general solution? Let's define that formally, okay? So definition. A solution to an nth order differential equation on an interval I is called the general solution on I. So the general solution on I. If two things have to be true. First, the solution contains n constants. Usually we call them C1 up to Cn. Okay, that's the first thing. And all solutions to the differential equation can be obtained by assigning appropriate values to the constants above. Okay, so these are two conditions that have to be satisfied. So something, you notice that these match, right? This nth order, and also the fact that there's n constants here. That's not a coincidence, okay? What this is saying is that if something is to be considered a general solution to an nth order, it has to have n arbitrary constants in it. And the second thing is saying that this has to have all solutions. In other words, no matter what solution exists, you can get it by assigning a value to those constants. Now, there is an important distinction here. Note not all differential equations have a general solution. An example would be, what about this guy? Y prime squared plus y minus 1 squared equals 0. You notice that the only way that the sum of two squares can equal 0 is if both of those arguments are exactly 0. So this guy has only one solution. So that solution would be the function y of x equals 1. Think about it. That's the only way that you could get a derivative to be 0, and for the second part, for y minus 1 to be 0. So this is an example of something that does not have a general solution. So one of the simplest differential equations to solve is the differential equation that looks like this. Okay, this is extremely easy because all you have is an nth derivative on the left and an f of x on the right. So how do you solve this thing? To solve, just integrate f of x n times. That's it, okay? Pretty simple. Okay, one more definition, or actually a couple more definitions. We're almost done with the definitions. Remember, we talked about a general solution. So a solution to a differential equation is called a particular solution. If it does not contain any arbitrary constants not present in the original differential equation. Okay, so the only way it can be called a general solution is if it has new constants that are arbitrary, like C1, C2, all the way up to Cn. If the only constant it has, for example, is a k, and that k appeared in the original differential equation, that does not count as a general solution. It would just be called a particular solution. Okay, so what is an initial value problem? Let me define it formally, okay? Let me put this on the next page. So definition. An nth order differential equation together with n, we call these auxiliary conditions, okay? They look like this. Y of x naught is equal to y naught. Y prime of x, these should all have the same input value. Y prime of x naught is equal to y1. Y double prime of x naught is equal to y2. And then y n minus first derivative of x naught is equal to yn. We started at the zero derivative. Yeah, this would be yn minus 1. That's right. Where yi, let me write it this way, where these guys are all constants, is called an initial value problem, or IVP. Okay, so let's practice solving a differential equation. In particular, let's practice solving an initial value problem. So example, solve the IVP. So an IVP means that I have to give you the differential equation, and then I have to also give you the auxiliary conditions. So we have y of 0 equals 1 and y prime of 0 equals 4. So these guys right here are the auxiliary conditions, okay? This is the actual differential equation on the left, okay? But it is called an initial value problem because it has these extra conditions on it. How would we solve this? Well, I hope you see that this differential equation right here is exactly in this form, isn't it? It's this form because we have a derivative on the left and just a function on the right. In this case, it's a second order, isn't it? So all I have to do is integrate both sides. So let's start by integrating it once. Y prime is going to equal the integral of 18 cosine of 3x dx, which is equal to what? I'm hoping you guys remember how to take your antiderivatives here. The antiderivative of cosine is sine, but you have to divide by that 3 that's inside of there, right? This is a linear substitution trick, I call it, or just do a u sub, let u equal 3x. So this is going to equal 6 sine of 3x. But I'm going to go ahead and call this plus c1, okay? We have a constant that we just gained, okay? And how can we figure out what that constant is? Use this condition, okay? I'm going to plug in 0. So this means that y prime of 0 is equal to, I know it's equal to 4 because of this condition, but if I actually plug 0 in to what I got above, I get 6 sine of 0 plus c1, which is just c1, right? 0 plus c1. So what did we get from that? We get that c1 is 4. See, we found the constant. So this implies that y prime of x is equal to 6 sine of 3x plus 4. What I did is after finding this 4, I plugged it back in, okay? So now I've got y prime, but I'm not done yet. I have to take another integral. So y of x is going to equal the integral of 6 sine of 3x plus 4 dx. What's the antiderivative going to be? Well, the antiderivative of sine of something is negative cosine, and I have to divide by that 3 in there. So I get negative 2 cosine of 3x plus 4x plus c2. But now we find c2, and I'm going to do that by using this condition here. Y of 0 is equal to 1, right? So then 1 is equal to y of 0 is equal to what? I'm going to plug 0 in. I get negative 2 cosine of 0 plus 0 plus c2, which is equal to negative 2 plus c2. So if I add 2 to both sides of this, I end up with 3 equals c2. Take this guy 3, replace this guy, and we get our solution is y of x is equal to negative 2 cosine of 3x plus 4x plus 3. Okay. All right, guys. Thank you very much for watching. I'll see you next time.